All right, what's up, AP Physics 2? It is time to get you into magnetism and electromagnetic induction. These should be pretty quick notes, so hopefully we won't be quite as long as normal, but you already know whether or not they're quick notes because you can see the timestamp on them. Let's do it. First thing is magnets. All right, we got to talk about magnets quickly. It's a little bit more than just quickly, I guess, but we're going to nail a couple things real fast. So, properties of magnets, they create magnetic fields. These exert forces. These are non-contact forces, and so they're one of the few. We've talked about two other ones so far. Think about them real quick. Gravity and then electrostatic fields, right? So those are our two so far. We've got north and south poles on magnets, and you see how magnetic field lines move between them. North is going to be, we're going to be out of north and into south. That's going to be our positive direction. So magnetic fields generated out of a north pole and into a south pole. To actually define it, it's a material. It's magnetic. It's going to always be metallic. A permanent magnet is a material that keeps its magnetic properties at all times, no matter what, even when it's not close to other magnets. There are other magnets that we can temporarily make magnetic. We can make some things magnetic short term by aligning some domains. We'll get into that in just a minute. But some ferromagnetic materials, as you see right there, there's substances that can be permanently magnetic all the time. So bar magnets, horseshoe magnets, whatever shape we make them, we can make them out of iron, cobalt, nickel, gadolinium, and a couple other things, but those are the big ones, iron being the biggest of all of them. Magnetic field lines, they're going to travel from north to south, as I mentioned, and they're strongest near the poles. They're always going to be strongest, but you know this already, whenever the lines are closest together. So again, we're running through these pretty quick because it's pretty quick material for us now. Like poles repel, unlike poles attract, just like our positives and negatives did in electrostatics. So again, an important thing to note here, if you break a magnet in half, and this is a very common question that comes up a lot, will you get two monopoles? And the answer is no. Breaking this big magnet in half still makes north and south poles for both of the pieces that are broken off. And we'll look at domains within this, and that'll make a lot more sense as to why. But you never get just a north or just a south pole if a piece of ferromagnetic material, so a metal, is magnetic, then it's going to have a north and a south pole always. Important to note. Oddly shaped magnets also have north and south poles, and so they'll attract and repel through that as well, right? So out of north into south still. This helps concentrate the magnetic field a little bit just on one end there, which is why a lot of times this is done, is because it helps concentrate the field and makes for potentially more or stronger magnets. Now, domains within magnets are what really helps them be created and what makes magnetic materials or potentially magnetic materials become magnetic. So they have magnetic properties, and some materials, they exert those magnetic forces, and that happens because of the parts within a ferromagnetic material known as domains. So if we look at this right here, we're going to consider this piece on the left right here just a random piece of iron. And within that piece of iron, part of the properties that make up these magnetic materials are known as domains. And we see how they're unaligned here. And so they're just kind of pointing all over the place. And this is why a metal can be held up by a magnet, because it has the potential, because it's metallic, it has domains within it, but they're not aligned, and they need to be aligned. Those arrows all need to be pointing in the same direction in order to make a magnet a magnet. So if we were to induce magnetism, just like we induced a charge in an electrostatics, we could bring a permanent magnet in close. All the norths are going to start pointing towards the south because those attract. And then all the souths would point away, and so forth and so on. And we could create a temporary magnet, or potentially, if it's a ferromagnetic material, a permanent magnet by doing this. Okay, so we must align the domains. That's the important part here. And again, we see those domains there, right here, right? Unmagnetized, magnetic. And now we've got a non-magnetic material. So that's really the new piece here that we're adding. Over here on the right, there's just no domains within it, okay? It's just a property of metals and potentially metallic materials, right? That allows for them to have domains within them that can be aligned later on. If we put multiple magnets together, you see here, these are two different bar magnets, and obviously opposite sides on opposite ends here, right? We'll say for the use of this right now that red is north, and so north and south, but we still have these interactions, and you can see the electric field lines with these little iron filings, and we'll do a lab with this. that set up all of that and show you where those are. So multiple magnets are also going to work together to form fields. And we see how over here, I'll move my head for just a sec, out of north and south, out of north into south, but over here we're out of north and into south, even though they're separate magnets, and north repel. And so we see kind of how those magnetic domains and those fields can be aligned up, and we'll get some practice drawing some of these as well. That is a big part of the magnetic portion of this unit. Quick reminder, and you've already noticed this, and I've already mentioned it briefly, that magnetic dipoles act very similar to electric dipoles, and so this should look very, very similar. Now, something that's really interesting is that within these ferromagnetic material, these magnetic domains can actually be unaligned. So if you were to literally smack a hammer onto a nail like this that is magnetized, you can get rid of that alignment by misaligning it and by changing the way that all of these materials inside are lined up. Now, the way that happens isn't just like you smack something and all of a sudden they misalign. It's because when you hit the top of this nail, you're actually deforming this whole nail. It gets a tiny bit shorter every time you hit a nail. As it goes into a piece of wood or whatever else you're nailing that piece of metal into, it gets a little bit shorter, gets a little bit compressed, and that actually jumbles up all of these different domains within it and causes it to potentially become demagnetized. So we see those domains again, unmagnetized. And I keep showing you this because that's pretty much the whole thing with magnets. Magnets part's going to be short, and then we're going to get into what happens when electric and magnetic fields work together. This is the electromagnetism part, and this is the important piece of this. Okay, we care about this a lot because it's how we make electricity. This is the very basis for how turbines spinning a magnet within a coil of wire and the general parts of how a turbine works. This is the science behind what does that and what generates and then helps spread electricity for us to use. So first, an electric charge, it's surrounded by an electric field. We know that. And then a moving electric charge produces a magnetic field. That's the new piece here. When we have a moving electric charge, a magnetic field is created. And you see right here a wire with a current moving through it, and then a magnetic field that is forming around that. Okay? That's the principle that we're looking at here, okay? Now, a moving magnetic field can also produce an electric field. The problem is the electric field isn't really what we want. So in practicality, this is the part that we care about because we're going to move an electric charge to produce a magnetic field, or we're going to move this magnet, right, then to produce an electric field. So I guess it kind of works either way, obviously. So we care about both ways, and that's probably a misstatement. So apologies there. But the point being, we're then going to gather this electric field and give it a set direction, which you know at this point is a current. Now, electromagnetic waves, I'm going to mention these briefly just because they kind of show how these things interact with each other. As you've got this electric field, there is a magnetic field that goes with it. So the blue up and down here is our electric field that could be generated. And then the red back and forth is the magnetic field. What's important are a couple things. First, as electromagnetic waves, these things travel together. Electromagnetic waves being a really small part of what's actually supposed to be on the AP classroom curriculum or the AP, College Board curriculum. But it's kind of hard to understand this stuff without it. So we're going to hit it briefly still just as a decent AP physics teacher, I can't skip over electromagnetic waves completely and pretend like I've taught you this stuff. So we're going to make sure we address it. Electromagnetic waves are things like radio waves, all the way down to microwaves. Light, visible light is an electromagnetic wave. And then we go all the way to the other end of the spectrum where it's really full high energy gamma waves and stuff like that. These all are an electric field and a magnetic field traveling together. And that's what's really important. So as the electric charge vibrates, it then creates an electric field that changes as well, and they change and move together. All right, and that's what's really important. So this is our electromagnetic wave. We're going to see this referred to a lot as an EMF. We saw EMF previously. This is going to be in a different kind of EMF, but it's going to cause an electromagnetic force, and that's what that EMF is, okay? So this wave traveling is powerful enough via radiation and things like that to actually transfer energy and cause some forces to be present. We're going to get into that here coming up. So electromagnets. This electric current causing that magnetic field can actually then create a magnet if we put a wire in the right setup. Okay, so what we can do is we can send an electric current through a wire, and that can then create a magnet as the current travels through it, because as we just stated, these things travel together. So what this actually looks like, and you've probably done something like this in a pretty rudimentary science class, is we take a current and we send it through a coil of wire. If we coil the wire tightly, close enough, all that kind of stuff, different number of coils, all that, we create a magnetic field that moves through this. And we've essentially created within this wire a magnet, all right, or a magnetic field. Now, there's not actually a magnet here because we don't have that ferromagnetic material in the middle, but if we were to put a ferromagnetic item in the middle here, we could turn it into a magnet essentially, all right? If you've got an actual iron nail, then you could make it potentially magnetic permanently, and that's really interesting. So we're going to do a bunch of stuff with this in lab. We'll use some iron, we'll use some other materials, some other magnetic material, or metallic materials, and see what does and doesn't make a magnet. Now, since these things move perpendicularly to each other, it's important to have an idea of what our directions are, because we know positive and negative is just direction in physics, but we want to make sure we define that. So if you have a wire right here, and this is the right hand rule, and we're going to practice this. So right hand, always right hand, that's important. And that's important because that's the direction we've noticed the field goes in. If you use your left hand instead of your right hand, you're going to be pointing in the wrong direction. So right hand rule, remember it as that. You're going to place your thumb in the direction of the current moving up here. So current moving up. If your fingers are straight out and then you curl them towards your palm, if the wire was in the middle of your hand, then the magnetic field that you see as you do that, so here's the current traveling through the wire's in the middle of my hand, this is the direction then of the magnetic field as it's traveling around it, not the other way. It's going in the direction that your fingers curl around the wire. All right, and with some practice, you'll find this to actually be pretty easy to figure out what's going on. So a little bit more with that, right? You see the hand right there and how the wire is in the middle of it. The way that those fingers curve around the wire shows then how that magnetic field is moving around the wire. So thumb in the direction of the current there. B is going to be our magnetic field. And again, that's going to be in the direction that your right fingers curve. So it'll be really fun on test day for this stuff. You guys are going to be doing this with your hands all over the place. And hopefully we're using our right hand to do that, not our left hand. In order to calculate that magnetic field, the strength of this magnetic field around a wire, we need to know the current and then the dimensions of the wire. So we'll get a little more into that right now. As with all non-contact forces, right, the strength is going to be based on how close you are to the source. And so that's what really our 2 pi r here is also, right? R being, I'm sorry, I said the diameter of the wire. Apologies. I'm trying to get these in really quick here, y'all, so I'm just rushing through this. So sorry about that. R there being how far away you are from the wire. So as you get further away, the magnetic field is going to diminish. And this is why every paper clip you've ever had doesn't get drawn towards every wire in every room, right? Because they're too far away from this. But as you are closer there, then it will get stronger. And as you're further away, that will change as well. And this permeability of free space, this mu0 is a constant that is on your equation sheets. We'll talk a little bit more about that as we get to it. Now, B, the magnetic field, this is measured in Tesla, and that is equivalent to 1 Newton per milliamp. All right? Per meter times amps. Yeah. Yes. Okay. Sorry. And if I'm confusing with that, we will clarify in class. My apologies there. And then so some typical magnetic field strengths in Gauss. Now, Gauss is a toned down version of a Tesla. A Tesla is actually big. It's a big unit. And so you'll see some Gauss here. Because some of these fields are pretty small, right? So the standard fridge magnet's only 100 Gauss, and then it takes 10,000 Gauss to be a Tesla. So that's a big difference, and so we tone it down a little bit just to make sure that that is correct there, and we can make that work. So magnetic forces on electric charges. We might have to bring this in also, but right, similar to electrostatics, magnetic fields, they'll exert forces on electric point charges and electric currents. So this is our quick reminder from electrostatics. I won't give you flashbacks. We finished that not long ago. But if you need to pause and look back through some of this stuff, we talked about interactions of point charges at different distances and how fields vary as you move away from them and so forth and so on. Same kind of thing is going to be happening here. There's actually going to be that force that pulls something. In order for two magnets to stick together and be difficult to pull apart, there must be a force pulling them together, right? So this force is known as the Lorentz force, and it's that magnetic force that's present when you have a metallic object in a magnetic field. All right, that force is going to be in newtons. Q here is going to be a point charge, so this is also going to have an effect on an electric charge because, again, they work together. So electric charges moving in a magnetic field, that's what this force that we're looking at right now, this Lorentz force, is referring to. Okay, so that's actually what we're calculating right here. And it's the charge, the velocity of the particle as it's moving through the field, and then the strength of the actual magnetic field. And that strength is in T Tesla. That's important to note too. All right, now the force is going to have a direction also. And so we're going to use the right-hand rule a little bit differently to determine this force. So instead of doing our whole curve here, what we're going to do is we're going to say, all right, we got our current. We're going to do this setup. We need a three-dimensional setup here, okay? So you see the finger pointed in the direction of the current. All right? Now the direction of the magnetic force is going to be found building this up, right? And so it's going to be, we're going to now have our magnetic force coming out this way, magnetic field, and a current carrying wire coming out with that middle finger that's straight out towards me based on the current being here, and the force pushing upward. All right, so we're going to have this three-fingered crazy rule going on here that's really like an extension of the right-hand rule that we looked at when it was curved before, and we can see the electromagnetic forces shown here so that the force is actually going to be pushing up if the current's going this way and the magnetic field is moving towards me here. So to make that maybe a little more visible, all right, now we have a force on the electric current as it's moving through the wire. That actual force on the wire that can cause wires to move and interact with each other here is going to be measured, and the force here based on the current, the length of the actual wire, and then the strength of the magnetic field generated. And you see how the force is moving upwards there, giving the current moving down the wire and the magnetic field into the page. This is a lot to look at here when we're not in a three-dimensional space, and we will build on this in class so that we can go a little bit further with this, okay? And obviously, I'll get you other resources. We'll do labs. We'll do all that fun stuff. Now, the important part of this is how we induce this. So electric and magnetic fields here, or electromagnetic field, you might see as well. But as previously explained, right, this is what we care about and what we want to make sure we can do. And so if we take this magnet, and Faraday was the first person to discover this, moving or changing the magnetic field within this coil of wire will induce a current. So moving this magnet up and down through the coil of wire here creates this current. Moving it up and down will create a current that's one direction and then the other direction, and this is how we get what's known as an alternating current, but we don't actually have to worry about that in AP Physics 2, so that would be for a later class for y'all. But not moving it then will create no current. And what we do then within a transformer, we're creating electricity, is we just find some means by which to move this magnet back and forth through a big coil of wire, and it creates a current. And all we do really is find some way to make that work. So whether it be a windmill spinning, or we burn coal and then evaporate water and the steam spins the turbine, whatever it is, we just want something moving back and forth through a coil of wire. It's as simple as that. Magnetic flux. This is important because this helps us more efficiently do this. All right. So the magnetic flux, this is the number of the magnetic field lines that pass through a closed surface, some conducting coil. So right here, we've got a surface with some area. There's a magnetic field bombarding this. How much or how many of those magnetic field lines, which is really just a measure of how much magnetic field hits this surface, is known as the magnetic flux. We want to try to maximize that if we're generating electricity. So measure of the magnetic flux applied right there. There we go. It's known as phi here. And so it's going to be the magnetic field, the surface area A of this surface that we're looking at. And you see this cosine theta because if we aren't aligned properly, then we're not going to be at the most efficient angle to make this work. Okay, so to look at that in a different angle here, this is what we're looking at. If we have a magnetic field moving between these plates, right? This same area right here, aligned perpendicular to that field, is going to absorb more of these field lines than this one that's aligned at an angle. And that's why the angle is part of the calculation and why we care about it. But ideally, we want to make it perpendicular if we're trying to absorb as much of this magnetic field as possible, and that's that magnetic flux. So why do we care here? First, a coil of wire moving through a field, this generates our current, right? And that's something we talked about a little bit. We'll get more into Faraday right here in a second, again, and the calculations behind that. But increasing the area within that field will induce a greater current. And so that'll work oppositely also. When we go way back to our coiled wire around a nail, we're going to want to coil that a lot, and thus we'll create a bigger magnetic field. So this works again both ways. And then changing the shape and orientation of a wire, like I just mentioned, within that magnetic field will have the same effect. All right, and we'll create either a bigger current or a bigger magnet if that's our goal. Now, Faraday's law of induction. This is our calculation for that EMF. N being that number of coils. And again, what we care about is that flux that we just finished talking about and how long it's being applied. That is what helps us determine the change in flux over a period of time. And this is our EMF that was mentioned earlier. So moving this quickly, this magnet quickly through there or slower through there will generate different levels of EMF. So right here, we're slow. We've got a current being induced, but a small one. Here, we're moving much faster. We've got a current being induced, but a much higher current. So that's important too as you generate electricity, because we typically want to do this as efficiently as possible. So we'll try to move the magnet quickly through this coil of wire and thus generate a higher current. Lenz's law states an induced current is in a closed conducting loop, will appear in such a direction that it opposes the change that produced it. All right. And so the direction of movement being downwards here, right, is going to produce a current that's going to move opposite to that change there. All right. And that's important when we get into a space like this. And this is the last thing we're going to talk about. So we'll build much more on this clearly, right? But as I move something here potentially through a magnetic field, this metallic device, I can move something here, even though we're not coiled this time, and induce a current. So in a circuit with an acting current, this EMF can also be generated by moving the conductor through a uniform magnetic field. And we see this again, our EMF here. It's telling me it's all spelled wrong, but this one might actually be spelled wrong. Another Mr. Berry special. But this EMF is measured in volts, and thus it acts as a source for the current. And that's really important there at the end. So EMF acting in volts, source for the current. We're going to build on this a lot. But in short, magnets generating currents is the big point of this whole unit. So hope this is kind of helpful. I apologize for rushing through this, but this is the time I had available to get it done. So we'll talk more about it in class. See you then.